So let's start by looking at the description of a gas. So we've talked about the different phases of matter: liquids, solids, and gases. Now, a gas is the phase of matter that is going to expand to fill up any volume that you put it in terms of a container. So it'll occupy the entire volume of any specific container that's holding the gas. Now, that'll mostly be empty space. You can compress a gas, though, and those gas particles, the different molecules or the atoms, will get closer and closer together. But in a normal kind of like atmospheric level of pressure, like the air around you right now, there's a lot of space between those molecules. Now, they're also constantly in motion, the molecules or particles that you have in the gas. They're going to move in a straight line and they're going to collide with each other or the walls of the container. And so they'll just collide and bounce off, kind of ricochet around. So the pressure of that gas is going to be the force of those collisions distributed over the surface area of the container wall. And now this won't include the collisions between the particles themselves, but the pressure that a gas has is going to be the collisions of those particles with the container wall. And so there'll be a lot of those because there'll be a lot of particles in our gas sample. And so that force applied over the area of the container walls will give us the pressure of the gas, the amount of force that's being exerted by the gas onto the container. So looking at the pressure of a gas, it's going to depend on a few different factors. First of all, the number of particles in that space, that container. The more particles that we have, the more collisions we're going to have with the container wall, just because there's more of them around. The volume of the container will impact the pressure as well, because if it's smaller, the same number of particles in a smaller container versus a larger container will, in the smaller container, hit the walls more as they bounce around. And also the average speed of the gas particles. We're not going to say that all the gas particles in our sample have the same speed. There's going to be a nice distribution of speeds that they'll have. But if we look at the average, is that average speed increases and those particles are moving faster, then they're going to hit the walls of the container more. And so we're really looking at how many times the container's being hit by a particle and that force, and it's going to increase as we decrease our volume, as we increase the number of particles, or we increase the speed that they're moving at. And so as we increase those things, or decrease the volume, we're going to see that we have high pressure. And so our pressure increases, as we described, more collisions occurring. And we'll have a lower pressure when we have less collisions occurring. So that's going to be when there's less particles around, or it's in a larger volume, or those particles are moving slowly. Here's how we measure pressure. We have a couple of different ways. Well, I mean, we have a couple different instruments, I should say. But the basic idea is that we assess how many collisions are happening against something that we know the density of. Mercury is a really common one because it's a dense liquid. And so if you're measuring the atmospheric pressure of the gas in the air around you, you're going to see the gas in the air collide with even something as simple as a bowl of mercury, liquid mercury. And as it collides, it'll push that mercury up a tube, and we can measure the height that it travels. And that'll tell us the pressure. Like, so the more pressure being exerted by the gas, the higher the mercury will travel up a tube. And so it's kind of like our most basic way of doing this. Another, like the in the lab, you would use a manometer, which is this one right here, which is the same principle though. We have a gas pressing down on mercury and moving it. If we have a gas sample in a manometer, it's going to exert pressure on the mercury that's going to push the mercury in a U tube up the other side. And so that's going to tell us the pressure relative to the atmospheric pressure that's pushing down on the mercury on the other side of the tube. And so from this, we can determine what the pressure is. And actually one of our units of pressure is millimeters of mercury. It's really looking at just how many millimeters will mercury travel up a tube in a vacuum based on like the gas pressure being applied to the mercury in a bowl or outside a manometer. A barometer is a more common tool that you will see in like introductory chemistry lab. Um, Research labs typically have manometers that are highly tuned to be able to measure the pressure of gases in a way that would be stoichiometric. In a lab setting for a chemistry class, we are more likely just going to need to know the atmospheric pressure at the time. And so that means just the pressure of the air around us. And so we can use a barometer for that, and it'll directly read the pressure of the air in the room around it. And here's an example of one that uses a needle. Some of them are digital reading outputs. You can Google the pressure in your city at a certain day, right? Like, so like, I think data is collected by UW and published. You can publish like, what's the atmospheric pressure in Seattle right now? You'll probably get something in millibars, which brings us to this idea of units for pressure, right? So we're talking about force over area. And I'm going to skip these. And we have actually a lot of different ways of expressing that pressure. So force over area, I mean, one of the primary ways to think about this is a Pascal, which is defined as a Newton force divided by meter squared, so area. Um, and that's what we define as a Pascal, and that's a unit of pressure. Now, we typically work in atmospheres in a chemistry lab, and that's atmospheres is another pressure unit. Not like the atmosphere around us, but like spelled the same way, but it means an atmosphere pressure. And it's actually equal to 101,325 pascals, or 101 kilopascals. And remember, kilo just is one of our metric conversions. So 1,000 pascals equals 1 kilopascal. Another useful conversion here, like you can reframe that in terms of like atmospheric pressure, like the common one. So 100 kilopascals is a common pressure to be at near sea level. It's about 0.9868 atmospheres. So there are other ones. I mean, if you think about in our daily lives, when we think about pressure, for me, the first thing that comes to mind is when I pump up my bike tires or test the pressure in my tires on my car. And both of those are going to be measures of pressure that we usually use PSI or pounds per square inch, right? Pounds of pressure per square inch. So that's one of our many units. For a conversion, 14.7 psi is equal to 1 atmosphere. So atmosphere, again, being the chemistry lab preferred unit for pressure. Other ones that we see are millimeters of mercury, which we use a lot in the chemistry lab as well. And again, that's coming from the direct measurement of how much mercury travels from the pressure of the gas or the atmospheric gases pressing down on it. Torr is another one, and 760 torr will be equal to 1 atmosphere. We also have bars and millibars. These are usually used in weather reporting. So 1.013 bar or 1013 millibar equals 1 atmosphere. And remember, 1 bar would equal 0.001 millibar. And that's again just our metric conversions.